Hello everybody and welcome back to the lecture. So we are discussing the synthesis of the nucleobases and how you can manufacture the nucleobases in the laboratory. And we have started with the synthesis of the pyrimidine nucleobases. Pyrimidine nucleobases, or it's not only the pure nucleobases, also their derivatives, because a large variety of those derivatives have shown interesting properties, biological as well as the pharmaceutical properties. And we have seen in the last lecture that you can formulate a retrosynthetic procedure for the synthesis of such nucleobases. And we have seen that if you have, for example, here a substitution, R1 can be any kind of substitutions, R2 can be any kind of substitution. Mostly we will take the simple substitutions that we have talked about. NH, CO, there is another NH here. So this is a class of the pyrimidine nucleobase, uracil or thymine mostly. And you can find out a retrosynthetic procedure means going back, and we have seen that you can do it by cleaving these two bonds and starting with this kind of compound. It can be either an ester or can be an acid chloride, things like that, with a good leaving group at the place of OET. R1, R2, and this is a carbonyl compound, plus very simple and readily available material, that is urea. So in general, this kind of compound is known as beta keto ester. So if you consider this is an ester, this is the alpha position, this is the beta position. So you have a carbonyl group at the beta position. That is why it's called the beta keto ester. So a combination of beta keto ester and urea. So this is the retrosynthesis. Now if you look towards the forward synthesis, if you start with this plus this, and we have seen if you reflux inorganic solvent, suitable organic solvent actually, that depends in the property of this compound in which organic solvent this will be soluble. You have to heat it up at a reflux condition, and in presence of strong base, either sodium hydroxide or ethoxide, followed by, sometimes it takes strong acid also, H2SO4, then you get the fusion product actually, and you have seen that this is basically a nucleophilic substitution reaction, and this one was basically a condensation reaction. There will be OH and then followed by dehydration. So it will lose one water molecule and give you the desired product. And this is what you are looking for. This is what is your target, which is same as this. So the idea is first formulate a retrosynthetic scheme, and then with the starting points you have to manufacture, you have to come down to the target molecule. So to verify or to validate whether the synthetic protocol that you have formulated is actually correct or not, or is viable or not. So that is why you have to do the forward process also. And this is very much the process or the methodology or the technique that industries used or the pharmaceutical companies use to synthesize a variety of the pyrimidine compounds, pyrimidine nucleobase derivatives in large scale. Later on we have seen that you can further improve the method, or you can make the method more useful with more variations by a slightly different technique, with starting with the same starting material, same urea, but instead of the strong acid or the strong base and the use of organic solvents, you could simply use, you can replace all those by a Lewis acid PF3, which is present usually in ether. So ideally it is the BF3 that is the active reagent, which is essentially a Lewis acid, which means the boron has empty orbital to accept electrons, and you can use microwave chemistry here and no solvent. You do not need a solvent here. Within 5 to 10 minutes of reaction, you get your desired compound with a really good yield actually. R1 and R2, and you can have a lot of variations there. So the reason you do not need solvent is because of the fact that in most of the times your starting beta keto ester, your starting material, this is liquid, this is in liquid form, and urea is in solid form. So when you mix them together, they are immiscible because urea is solid and urea is not soluble in this liquid. But once you heat it up, once you start heating that up, once you reach the melting temperature of the urea, then it actually dissolves, it gets melted and dissolves it into the liquid form of the beta keto ester. So then they come in the single phase, and therefore they can do the reactions without any organic solvent. So this is one case. Secondly, if you want to synthesize the little bit modifications which we have done as R1, R2 in here an amine, so this is called, if you do the numbering, 3, 4, 5, 6, this is 2 amino pyrimidine. And this is basically an isomer of cytosine. If you see, this is your cytosine, here the amine is present. So it is just that the amine group in the 4th position of cytosine has come down to 2nd position, and the keto group at the 2 position of the cytosine has gone to the 4th position. It is an exchange kind of thing. So this is your cytosine. So this is called isocytosine. So cytosine can be synthesized from the starting material. Here would be cyanide, CN, and this. If you have R1 and R2, you will have here R1 and R2. In general chemistry I am talking about. For cytosine, R1 equals to R2 equals to H. Both are hydrogen. This plus urea, combination of these two under the similar condition as we have seen before will give you the cytosine. Now the variations and the unnatural one, this is mostly unnatural isocytosine derivatives. They are, many of the medicines have this kind of structure, this kind of component in the total molecular structure of many medicines actually. So you can manufacture this by cleaving here and here. It will come down to the same thing here, beta keto ester, beta keto ester, R2, R1, plus here if you see, this should be, instead of urea, this should be this molecule. urea had one oxygen here. In this case you will have, because you have to bring the NH2, so you will have the NH moiety here. This is known as guanidine. This is called guanidine. So a fusion of guanidine with the beta ketoester will give you the 2-amino pyrimidine that we have discussed already in the last lecture. So if you want to do the forward reaction with this 2-amino guanidine, and this compound mainly exists when you buy commercially. This does not exist alone because it exists in terms of salt, most of the times in terms of the hydrochloride salt. So this compound exists as .HCl, and when you fuse them together, obviously first thing is that the HCl will otherwise interfere with your reaction, so you have to remove the HCl. Therefore you need to use a base in this. But you do not need to use a strong base. What we have figured out that if you use a mild base, just like BF3 was a Lewis acid, potassium carbonate is a Lewis base, LB. It's a mild base, so it can actually neutralize the HCl over time, and then it will give you the same kind of, it's a nucleophilic substitution, and this one is your hydration. Dehydration will occur here. So you will have this in H, in here you will have the NH, and you have NH, R1, R2, there will be OH here, there is H here, so followed by minus water, so I am showing you the forward process actually. R1, R2. Now here you can see that this is the imine form, so it will undergo tautomerism very quickly, and will give you this NH, because this will be the driving force is the aromaticity. Yeah. Your target compound 2-amino pyrimidine or isocytosine. So likewise you can make a lot of variations. You can change this into sulfur, and here you can make sulfur. So many variations that are present in our organic library actually and are commercially available also. So you can find out the proper synthetic scheme depending upon your target molecule. So this is what you can do in your laboratory. By the way, do you know how these pyrimidine nucleobases are synthesized or biosynthesized in living cells? It's usually the cytosine which is first synthesized. NH. This is your cytosine, and then this is converted into uracil. It's a pretty easy hydrolysis reaction basically. So this conversion happens with the help of an enzyme called deaminase. Here enzyme, of course in biological cells everything is catalyzed by enzyme. So in this case enzyme is deaminase, cytosine deaminase we call. So there are variations. So it's one kind of deaminase which will deaminate the cytosine, remove the NH2 group and will hydrolyze to the keto. So it's basically a hydrolysis reaction, essentially an hydrolysis reaction. that will convert the cytosine into uracil. So, even if you keep cytosine in your laboratory in proper condition, in aqueous medium and little bit with the condition, maintaining the conditions, over time you can see the cytosine will be converted or will be hydrolyzed into uracil. And once uracil is synthesized, this is then converted into thymine. And this reaction I have mentioned before also, this reaction is catalyzed by an enzyme called thymidylate synthase. Thymidylate synthase. So, that is how in biological cells the thymine is synthesized or uracil is synthesized. Okay. Now, this is in biology. Now, what about the real molecules, these molecules that have been evolved? So, if you ask a question, how come these molecules were evolved when there was no biomolecules, when there was no biological cells, when there was no biology in fact? I am talking about prebiotic chemistry. Prebiotic chemistry. Prebiotic means before the biology, when there was no living cells, there was no living thing in the world, in the earth. So, we are talking about millions and millions of years before the earth was evolved, before the biomolecules were evolved, before the living organisms were evolved. So, what was the starting point? How the molecules were synthesized from the materials that were there present before the biology? There was no enzymes, in fact there were no biomolecules there, and there were also no larger molecules, only the smaller molecules were present. So, a popular theory is that before the earth, I mean at the very beginning of the earth, that is millions and millions of years ago, everything was in a very molten state, kind of liquid form, that is being called as primordial soup. If you have not heard this term, you will heard this term quite often if you try to read the evolution of the molecules or evolution of biological molecules on earth. So, primordial soup is considered as the molten state at the beginning of the earth when earth was created, because there was the temperature was very high, there was a lot of pressure thing, and sparking were there. So, yeah, and there were very less amount of air, oxygen was very less. So, everything was in kind of anaerobic condition, and this is the whole thing is called the primordial soup. So, we will now see how some experiments have been performed to validate some theories that explains, that will kind of give you ideas how the nucleobases were synthesized out of this primordial soup. So, when there was no biological cells, when there was no protein, no DNA, a basic question is how the living cell was created first. So, such a long kind of molecules, the proteins and DNA are very large molecules, and therefore, they are not easy to synthesize when there was nothing. So, obviously, they had a starting point. And again, a popular theory that is known as RNA world theory, that predicts or that kind of gives an hypothesis that RNA was the molecule which was created first. RNA was the first biomolecule which was created first out of all the other biomolecules. And from RNA, the other biomolecules were formed, and then came the single cell, single living cell, kind of amoeba kind of the living cells were created. So, now in order to synthesize the RNA, you have to synthesize the nucleobases. So again it comes down to the fact that how the nucleobases were synthesized at the beginning of the earth, which is we call prebiotic synthesis. So now I will show you two beautiful experiments that have been performed. There are many people actually, there are many research are going on to understand or to predict this problem, that how what exactly happened, how the molecules were evolved. And of course that has a big problem, is that it has happened over millions and millions of years. So if you want to do experiments in the laboratory, you cannot spend that much time, or you cannot afford that long time to your reaction mixture to understand what could have happened. So you have to create a simulated kind of atmosphere in your laboratory to understand such factors, and therefore that makes it tough, because the time is a big issue here. The reason is, when there was when the small molecules were present in the primordial soup for millions and millions of years, they had high degrees of freedom. And of course over time, I mean, if you think of that long time, then the chances are pretty high that at one time or some other or the other time, the molecules will come close together and they can do chemistry, and that time frame is difficult to spend in the laboratory. So they have kind of simulated the atmosphere. So first experiment I will show you was published in Nature, the famous journal, in 1995. This is the volume number, you can search for it, 375, and page number is 772. So that has actually tried to understand how the nucleobases were synthesized, and they have started with the simple molecules. So at the beginning of the earth, all gaseous molecule on salts, liquid, solid, everything was composed in a soup, and there were mostly lot of gases were present obviously, and very less oxygen, as I am saying. So it is very clear that the methane was present. Carbon dioxide and carbon monoxide both were present. So in this case they have taken methane and nitrogen. What they have seen, if you take methane and nitrogen, so this has been validated by other literatures also, and with high electric spark discharge, you can be able to synthesize an organic compound, which is an acetylene derivative, acetylene and cyanide. So this is cyanide, this is acetylene. This is quite well studied actually. Many literatures have reported this reaction that happens. So this is a key compound now in our hand, and from here I will show you how the nucleobases can be synthesized. So if you start cyanide and basically hydrolyze it with water. So it's like, if you have, the organic chemist can understand it very quickly. If you have acetylene and if you treat it with H2SO4 in acid condition and water in acidic condition, then what you get is the hydrolyzed product, that is CH3CH1, an aldehyde. So here if you treat it with water under certain experimental condition, then what you can have is this compound, so aldehyde. So this should be converted into aldehyde. This would have been CH2, because free acetylene would be CH3, here it is already bonded, so it will be CH2, and you will have a cyanide as usual. And now if you react with urea, urea is a small molecule which is easier to synthesize or easier to be evolved from ammonia. Ammonia and carbon dioxide or carbon monoxide actually produces urea, that is also quite well known. So if you react with urea, then what will happen, Now you are close to the cytosine kind of synthesis. This, so you will have N, it will be H, here NH of urea, NH2 aldehyde. Now this can do the same reaction as you have seen before, and I am skipping the step, so it will be minus water, and you will have NH, and obviously this is the imine form, so it will tautomerize quite fast. Your cytosine is ready. So cytosine can be synthesized from this molecule, and obviously this molecule came from only methane and nitrogen. So once you synthesize cytosine, of course you can synthesize the uracil after hydrolysis. This would be hydrolyzed or deaminated. Uracil was synthesized. So that is an experiment that actually kind of suggests or gives you a hypothesis how the molecules, the nucleobases could have been evolved. There was one second experiment that I will talk about, another beautiful experiment actually, and this was published in Nature Communication, another very high profile journal, in 2019. So what they have done is they have tried to synthesize the nucleobases in interstellar ice. So the ice form in the other stars or other stellar systems where there is no life yet can be a good mimic or can give you idea how the molecules could have been synthesized on Earth, because I mean people kind of think that the same molten state or the same kind of molecules that are present in the interstellar ice form or in interstellar systems were present also on Earth millions and millions of years ago when the biology was not there on Earth. So studying the interstellar system and trying to find the evolution from there could have been a good mimic. So and again obviously you do not have interstellar ice in your hand in your laboratory, so you simulate in the laboratory what the same composition that would have that are present or that have been already studied by the scientists, that these kinds of molecules are present in the interstellar systems. And interstellar ice is composed of water, carbon monoxide, ammonia, methanol, and all sorts of stuffs. So people have used the same composition in the laboratory and tried to find out whether you can synthesize the nucleobases. So what they have done in this paper is that they have taken all of these, and of course at the beginning of the Earth there are a lot of radiations, there are a lot of UV radiations, intense UV radiations were there along with high heat, high temperature. So they have used a high UV radiation in this composition. They have taken a composition of this all these molecules and they have started irradiating with high UV dose. Whatever they have obtained after that, they have processed it further with high temperature. Because that was there in the prebiotic earth. And after this, they have tried to find out what are the molecules that have been formed. And guess what? They have isolated all three of the pyrimidine nucleobases. They have isolated cytosine, they have isolated uracil, they have isolated thymine. All three of them were present in the final composition after this reaction. Not only that, plus some of the purine nucleobase derivatives like adenine guanine derivatives were also found in this experiment, purines. I will give you some structure. So, adenine was there. Out of these purine bases, adenine was found, and then this compound should be 5-membered. NH, OH, N, double bond, this is N here. This is hypoxanthine, xanthine. So, one kind of purine. They had also guanine that was found, and then xanthine was found. This is xanthine. This one was also found. So, a mixture of the purine bases were also found in the same reaction mixture. So, this kind of chemistry actually tells you to develop more hypotheses or more predictions of about the fact that how the molecules could have been synthesized, how the basic subunits of the biomolecules would have been synthesized from the prebiotic earth, from the when there was no life. So, similarly, we will see some prebiotic chemistry later when we will see the amino acid synthesis. So, now you have the pyrimidine kind of pyrimidine synthesis. Now comes the purine synthesis. So, pyrimidines you can synthesize in the laboratory. Now comes the fact that how can you synthesize or how can you find the retrosynthesis retrosynthetic routes for the purine nucleobases. A general structure of the purine is this. Here the sugar would be attached. So, this nitrogen has to be free, has to be NH. Here can be any derivative, usually there is nothing here, but I am keeping R so that you can have variations. Here there is N, so R2 depending upon the nucleobase they will vary, and N, another N. So, if this is the structure of a purine, how can you synthesize the target molecule? Now, if you look at the molecule and if you think of the pyrimidine kind of synthesis, of course, you now know that this 6-membered ring you can synthesize very easily. So, one of the idea can be that you start with the 6-membered ring and synthesize the 5-membered ring on top of it. In other words, you have to synthesize this 5-membered ring on the pyrimidine. So, now if that is the approach, I call it approach A or route A. So, then you have to think of how to synthesize the 5-membered ring. Now, where to cleave the bond? As we have seen before, the cleaving the carbon heteroatom bond is the easiest one, is one of the easy tactics that can be used in organic methodology. So, in that case, it could be that this bond can be cleaved, this bond can be cleaved, and the whole thing can be attached to it. So if you do that, then there is an issue that I have already talked in the last lecture, that then you have to fuse, you have to form the CN bond, you have to form this CN bond also with an aromatic ring, and now aromatic ring is already high in electrons, electron rich. So doing chemistry or making a new bond formation with the aromatic ring with an other electron rich center is hard, because nitrogen is electron rich, aromatic ring is also electron rich. So this bond formation would be little bit harder. Possible, there are a lot of methods are there. This is little bit harder. So the easier way to do is not to touch this bond, not to touch this bond. So but to cleave this, if you cleave this bond there, so what you will get down to, and if you cleave this bond here, then you can start with this amine here, this amine here, and in this case what will be in the other compound, you are forming a double bond. So obviously there has to be a double bond O, because remember it was dehydrated and formed double bond. So that could have been here, and here is a simple nucleophilic substitutions. So you can add just a leaving group, good leaving group here in this case. All right. So this plus this, you can using these two you can manufacture the purine. The other approach is you start with the 5-membered ring and then synthesize the or develop the 6-membered on top of it. So that is approach B. So you start with this and then develop the 6-membered. Again you can avoid the direct synthesis here, because this is also aromatic. So this bond should not be cleaved, this bond should not be cleaved. So you can chop off this or you can chop off that bond. So that will tell you you have R1 and you have to form this double bond. So it should be a double bond carbonyl, it's a carbonyl compound, and in this case what can you have? You can have amine plus the R part R2. If this is amine and there is a double bond here, so there has to be a carbonyl compound in this case, and this has to be manufactured, so there has to be an amine, kind of this. So these two can give rise to the purine, or these two 6-membered ring and this molecule can give rise to the same purine. So these are the two approaches that are more viable. So that is given here. If this is the ring, then you can cleave path A and this is path B. Now how to do the forward reaction? So starting with this, let's move to the forward direction. If we take this molecule in, I am starting one of the starting materials plus H, then what can you have? You reflux, almost the same condition, and heat in organic solvent. Then what we will have is this one will react, it will come down there. So if you do the mechanism, you will see that you can form nitrogen NH here, double bond, OH will eliminate. So you will have amine, this compound, and this is your guanine. Now you can see that there is another extra amine here which sometimes interfere with the reaction system. So in advanced chemistry you may need to protect this amine. Most of the times you do not require, because this amine does not react that drastically. So normally if you use these two, you will get the certain amount of the guanine. Now if you think of little bit variation, this if I start with and if you treat this with urea, can you find out what the compound going to be? So in this case, one of the amine would be a leaving group. This would leave, and then the dehydration will occur. What we will have is NHCO, NH2 and NH2 here. NH, there should be NH here, this, and then a second displacement of the amine group will give you a double bond over here. This would be NH, this should be NH, this compound. If you treat this with ammonia, then this carbon will get aminated actually. It's quite easy reaction. I'll tell you why we are doing this. Then this would become amine, and this would be double bond here. So ideally you could have started with this compound also here, and you could have get down to the same these two molecules would have been identical if you would have started with this, with the amine group already present. But in order to avoid the reaction of this amine, we have started with the double keto form here, and then if you need an amine, you can always do the amination by treatment with ammonia. So this compound, this is a guanidine derivative without the double bond oxygen here. This compound particularly is known as 8-oxo-guanine, because this is the 8th position. 8th position there is an oxo group. So 8-oxo-guanine. This molecule is actually present. It's a very notorious molecule which is created from the DNA. Or we call it the DNA lesions. The damage of DNA creates this molecule. This molecule is the reason why certain cancers are formed. It induces the mutations, and that we will see later. 8-oxo-guanine is formed by oxidation of guanine that is present in DNA, and this creates a mutations that causes the cancers. A lot of different kinds of cancers such as lung cancers, pancreatic cancers, they are because of this formation of this molecule 8-oxo-guanine, so which you can actually synthesize in the laboratory in this way. So now second, if you start with the 5-membered ring, how can we develop the 6-membered? NH here, and if you start with the amine, this, instead of this amine, it can be any other leaving group also. You can start with an ester as well, or acid chloride as well. If you treat it with formic acid or reflux, I am giving just one example. You can change, you can by varying this reagent, you can make different compounds, different molecules. Then what this will do is, this amine would react and would give you NH CHO, and of course now this reaction can take place. So you will have the 6-membered ring and then the 5-membered in here, in here, and then it can be NH, it can be H here. Initially there will be double bond here, then now it can actually tautomerize. You can write it in any form you wish, this. So this would be formed. Initially there would be double bond here and it will be tautomerized into this. So that is the way you can produce the, you can start with the 5-membered ring and can produce the 6-membered compound. So this is your basically adenine compound. Now the same adenine, so you have synthesized it from the 5-membered ring. If you want to synthesize the same compound from the 6-membered, then you can start with this. Here the amine, nitrogen, NH. So this compound, you can treat it with the same formic acid, or as you have used this format, ethyl format, or ortho format. Any one of them you use, you get down to the same compound, that is an aldehyde fused with the amine group. This would be produced, and of course then followed by dehydration minus water. Then double bond here, this would be NH, there was the double bond present here, this. If you go back to the prebiotic, I will give you one example, how the purine nucleobases, obviously you have seen one, that the mixture of ammonia, carbon monoxide, on all these things have produced the pyrimidines as well as the purines. There are other method that has explained prebiotic synthesis of purine nucleobases basically, and this one is actually very interesting. It all started with the HCN, hydrogen cyanide, and it's basically a polymerization of HCN. Means that many of HCN molecules were added together one after the other and form the final compound. We will see how adenine was developed. So first, if you have HCN and treat it with another molecule of HCN, So HCN is basically an acid, so which is H plus, Cn minus I am writing, so it can be protonated, and then so if this is protonated, then what you get is HC and H plus, and then Cn minus would react here, eliminating this. So you will have, in this case if you write NH double bond CH and cyanide, this molecule. Now this can further be protonated and will produce, so this will further protonate, will become NH2 plus, this will move, and there will be another Cn minus would go, basically this form. So this would be NH2, this is cyanide, there would be another cyanide here. Now once you form this, now you have a nucleophile amine which has a lone pair of electron. So cyanide is also electron deficient, it acts in both ways. So this lone pair of electron can attack the cyanide carbon and eliminate this. So in this case what you will find is the cyanide, this NH, H, this is CH double bond N, N minus, and there is one cyanide here. Now this minus can react here, eliminate this. So now you have a 5-member ring with N, there is a double bond here, carbon, then you have NH, cyanide, and in this case you have double bond NH. Now this double bond NH would obviously become NH2 by tautomerism. So this would be NH2 here. So here there is one H, so this can tautomerize NH. So you will form this compound. I have to write again here N cyanide NH2, there is a double bond here and an NH. So this react with another HCN, so obviously here, and this will come down, N, NH, C double bond N minus, rest is all the same, NH. Now this can go here, and if you do the whole thing, then you will see that you have, so this will be double bond NH, and this is your N, double bond N here, NH. Now this will all tautomerize because this has to be NH2. NH, this will become NH2, and this will become N, this will be another double bond here. So which is your adenine. So that's how you can synthesize whole of the purine nucleobase adenine out of the HCN cyanide. There are other purine nucleobases also were explained how you can synthesize them from HCNs. So, I mean, this is just one example of showing how the prebiotic chemistry could have taken place for the synthesis of the purine nucleobases.